first start, I want to apologize about my little contribution to semantic confusion by using the A word in the title of my presentation. I heard a rumor that they're going to start limiting use of Agile in presentation titles next year, so I wanted to get it into mine this year. but really what I'm going to talk about is my experience with improving the performance of software and how some of the lessons I've learned as an Agile developer have helped me in that task. Feel free to ask questions at any time, and I think we'll have some time for questions at the end. But if I get too focused on a rant, just wave at me. My name is Mike Stockdale. I'm the principal consultant for Agile Software. I do work with large corporate and government clients and enterprise applications, working primarily in object-oriented design, automated testing, and performance tuning. I also do some work in the open source area. I'm the lead developer on fitness.net, and my new evolution of that, FitSharp. So you can contact me in my email or see me as Jedi Whale on Twitter, or see my open source work at GitHub. So my biggest problem with starting a presentation at 2 p.m. is I know that the blood supply is just starting to divert from the brain to the digestive tract at this point. So this is my office at the Agile World headquarters, and I compensate for that mid-afternoon cycle with a little place to have a nap here. But if anyone really needs to, there is a nice couch out there, and I won't be upset if you want that. I was going to do this whole who's here, who's a developer, whatever, but I think in terms of the focus of this talk, the best question I could ask is, how many people here would rather watch This Old House as compared to Oprah? Okay, yeah, so the one thing I can guarantee about this talk is you will not hear the phrase nurturing self-actualizing teams. We're going to talk about software, which is my passion. I'm going to start out by talking about 3 different systems that I worked on. Never get one of these cheap little Dell remotes. There we go. First one was a corporate financial planning system. So this system, for a large corporation, began by pulling actual data from accounting in a monthly extract. And then the planners would create and analyze scenarios online. So they would enter rules like, we think labor costs are going to be flat this year, but transportation costs are up 5%, and production from this field is going to be down 10%, and production from that is up 5% from last year. So all this massive amount of data, of rules that they would enter online, and then they wanted the system to tell them what expected expenses and revenues were for next year, and analyzing all these different scenarios online. So we had a big design focus on trying to improve online performance because there was a lot of work we were asking the system to do online. So, what kind of performance problems hit us in this system? First time we tried to run our monthly overnight extract, we actually didn't let it run for 100 hours. We let it run for 4 hours and realized it was only 1/25 of the way through, and so it was going to take 100 hours to lapse. Okay, so here's my problem. Rail traffic control. Rail traffic control is sort of what it sounds like. It's like air traffic control. It stops 2 trains from running into each other. And at first you might think, well, that's not such a big deal. I mean, it's not like a train is a big problem, but not like air traffic. That's really an issue. But the there's a couple of things about trains. One of them is they're on tracks, so they can't veer out of the way at the last minute. So, in air traffic control, if things break down seriously, you still have that hope that at the last minute, the two pilots will see they're on a collision course and they can veer out of the way. With a train, you can't do that. And given a stopping distance of 2 or 3 miles, when a train engineer goes around the curve and there's a maintenance crew sitting there working on the track, he has nothing he can do. He's going to run them over. So this is safety critical, life critical systems, critical availability and response requirements. So the RTC stations had local data repositories so they could survive network outage. Asynchronous server updates so that again there would be no delays. So a serious amount of work in architecture into making this thing perform as well as be available. And of course, where did we run into an issue? We're trying to save the local repository. This was the thing that was going to save our bacon with performance. And instead of taking 1 second, it was taking 5 to 10 seconds. Okay, one more system. Now this one should be easy. Nothing can go wrong with this one. Banking data extracts. System-to-system interface. So no user there to worry about response time or availability. It's overnight execution, so it doesn't matter how long it takes. And here we're dealing with less than 10 million rows, so no way we're going to run into this 100-hour type of thing. Well, the speed was really great. Within about 3 minutes, we ran out of memory on a machine with 3 gigabytes. So welcome to the twilight zone of enterprise application performance issues. All of these things, when I first encountered them, weren't just something I hadn't designed for. It was something I couldn't even fathom. How could this be the problem? It wasn't not even where I expected it to be. And in all cases, the system is basically unusable. It's not a case where, users can put up with a little delay in response time. The system was unusable. We can't compress 100 hours into overnight, no matter how patient the users are. We can't accept greater than 1 second response time on rail traffic control. Now you might say, the users can just be patient, but given the life-critical nature of that system, the rail traffic controllers were not allowed to have that distraction enter into their mind. And so if the system could not deliver reliable response time, it could not be deployed to them. A couple of definitions. Enterprise application. This is a definition that Martin Fowler came up with at the beginning of his book on patterns of enterprise application architecture. So systems with large volumes of persistent data, systems with multiple concurrent users, lots of UI, and integration with other apps, complex business logic. Now these have a couple of implications for us when we're talking about performance tuning. Because there's lots of UI, because there's complex business logic, we're constrained in some ways in what we can do to these systems. I've heard the story about Twitter. I don't know if it's true that the initial version had a very simple, naive architecture, and when it became popular, they simply threw it away and rewrote it. Because what's the UI in Twitter? I mean, it's dead simple. You could rewrite it over the weekend. So for them, the fact that they had a really popular service that had severe response time requirements, they could just throw it away and rewrite it with a new architecture. They may have done that several times, for all I know. But with an enterprise application, you have so much stuff there, you can't just throw it away when it's slow. You need to deal with what you've got. Similarly, if there's some business feature or some business logic that's poorly performing, you can't just say, we won't offer that feature to our users, like a Facebook might do, for example, or a Google. If it doesn't perform, okay, we just won't roll it out. In this case, you're driven by business rules or government regulations or something like that. You have to implement certain logic. So again, you're more constrained than you might be in other situations. Performance tuning. I I guess, kind of obvious is making it go faster. But really, the hardware's working as fast as it can. We're not making it go faster. We have finite resources, so we're trying to optimize the use of those finite resources within some constraints. And most typically that constraint is elapsed time. Although, as we saw in my third example, it's not always elapsed time. Sometimes it's something else like memory. So why do we tune performance? More particularly, why do we tune software performance? Why don't we just throw more hardware at it? I mean, these are a couple of actual quotes that I've encountered. Well, hardware doubles every 18 months, so why do we need to worry? Well, that's fine maybe if you're deploying in 18 months, but that doesn't sound too agile to me. And maybe doubling isn't the kind of improvement you need. When you're looking for an order of magnitude improvement, like trying to get my 100 hours down to overnight, even if I could wait 18 hours, I'm still only at 50 hours, so hardware can only do so much. Here's another actual quote I've heard. Well, the production server is much bigger, so don't worry that in development and test that it's slow. It'll be much faster in production. Well, yeah, but so is the production database, so is your user base. And have you measured how much faster the production server is? Do you have any realistic hope? So typically, especially in enterprise applications, adding more hardware, adding faster hardware, going onto a bigger machine may get us a little bit of the way there, but quite often it's not the solution. We have to get into the software. So we'll talk about 3 approaches that I have tried over my career. First approach is back from the good old big design upfront days. So we get requirements from the customer. We've designed all the screens, so we go around, give them a list of 45 screens and say, what response time do you expect on screen ABC? And screen ABE, and screen ABE. And get them to fill all that out. And then we get to the fun part. My degree was in mathematics. When I graduated, I realized really nobody wanted to employ a mathematician, but I had taken some computer courses, so I ended up in this business. But this was the one place when I could dig out all that fancy math stuff that I used to. Build a mathematical performance model. We get to use Poisson distributions and queuing theory and all that kind of stuff and calculate what is going to be the expected performance given these requirements, given these capacities. And then we can assign resource budgets to the developers. So say, okay, you're doing screen ABC, you're allowed to do 5 database calls. The great thing about this is we're able to predict up front what performance is, a guaranteed reliable performance. Well, that was a theory anyway. The problem is, of course, the customers don't know the requirements. They don't even really have a full understanding of what screen ABC does, let alone what their response time requirements are. So typically they go back to the last project that someone was on and, oh yeah, okay, inquiry screens, those are always 5 seconds. And update screens, those are always 10 seconds. 1 second. So they basically give us meaningless input. And while the math is fun, of course, if the input into it is garbage, so is the output. And even if we could model this reliably, the developers are going to ignore you anyway, because they just want to get the damn screen done. For you, as some kind of performance architect saying, oh, and you can only have 5 database calls. I want to do all the damn database calls I need. So, of course, this approach doesn't work. The other approach is, perhaps you might call it the head in the sand approach. And I've heard people proudly proclaim that we're going to make it work first, and then we're going to make it fast. We'll focus on functionality. We'll build the entire system. We'll get it all tested, accepted by the users. Then we'll look to see if it needs performance improvement. So at least we don't waste all this time up front. But the problem is, by the time we start looking at performance, our basic architectural decisions are locked in. There's no time for clean code, for design, for testing. the only thing left to do is to call in the superhero. So this is the guy who gets to show off his technical prowess on the first day after the system goes into production and performance is horrible and there's a big panic and you stay up all night for the next 3 days and you finally find some kind of hack that'll make the system run faster. And you're the hero. I can tell you from personal experience, it feels really good at the end of that, and it can be quite lucrative too. But it's not really a sustainable way to carry on. I was reminded of this, I don't know if any of you were at Robert's presentation yesterday when he talked about how we're really all just apes dwelling on the savannah. And this is your chance to be the alpha ape, because you're the superhero who fixed this. Okay. So then we still need to look at a better approach. So what principles from Agile might help us? First one is the idea of last responsible moment. So this talks about decisions as late as possible. Not just because you're lazy, but because you want to wait until you have as much information as possible before you make a decision, because that increases the likelihood that you can make a good decision. But then the responsible part comes into that. Don't delay making a decision beyond the point where you can do something about it. So waiting until the entire system is built where you have, and goes into production, where you have perfect information about the performance problems, is too late. So we can't predict up front. We don't want to wait to the end. What we need is some kind of continuous process where we can measure and gather information as we go. We can start making improvements before it's too late. So that's the first kind of characteristic we're looking for. One of the other major principles of Agile is frequent feedback. We deploy early and often. If we can get the software into the customer's hands, if we can start to exercise it in some kind of close to production-like environment, we can start to see where the performance problems are before it's too late. The customer won't be able to tell you if you give them a list of proposed screens or screen designs what kind of performance they need. But if you let them have that software in their hands and let them run through it, they can tell you where it's too slow. Now, frequently with Agile, even though we're producing software every week or every 2 weeks, only in extreme cases are companies actually deploying to production every week or 2 weeks. So what we want to do is, whenever we develop runnable features in each iteration, we want to get them into some kind of production-like environment, or as close to production as we can, so that we can give do as realistic testing and get as realistic information as we can. I'll talk a little bit later about that. The third thing we do in Agile development is we're test obsessed. We have tests, unit tests, to test small pieces of our code. We have acceptance tests to test larger pieces of our code. And this gives us some tools that can be really useful when we're trying to measure performance. When we get some information from a customer, this part of the system is too slow, we then need to work our way down and find out where it's too slow. And if we already have this existing framework that lets us execute and exercise smaller or larger portions of our system, it's not that hard to think about that we might be able to adapt that. All we have to do is just measure how long it takes them to run, and we can use that information to guide us. And finally, we're trying to embrace change with Agile. So we have tests to keep our functional behavior unchanged when we're refactoring. We try to use design principles that limit the impact of change by single responsibility principle and the other solid principles, all of which are around the idea of encapsulating specific functions so that if one needs to change, there isn't a ripple effect. So if we're able to identify a performance bottleneck, then we have an analogous kind of technique where with refactoring, we are preserving functional behavior but changing the structure of the software to improve its understandability or its usability or its flexibility. With performance, we have the same constraint on the other side, that we're making changes to software without changing its functional behavior with an aim to improving its performance. So many of the refactoring techniques have a place when we're looking at performance tuning as well. So, this gives us some principles to use as our foundation to start thinking about what our third way of performance tuning might be like. So the first thing we need is to get this feedback loop closed, to get information from our software about how we think it's going to perform in production. And I talked previously about trying to get into a production-like environment, a test environment that's as close to production as we can get. Ideally, we'd like to develop some kind of scaling factor, so we can map the observed behavior in our test environment to a predicted behavior in production environment. So this is a little bit like, the production server is going to be faster, but to quantify that, to say, well, actually it will be 1.5 times faster, or it'll be twice as fast. There's a couple of ways we can try and get that kind of number. If there's an existing system that's in production, similar kind of hardware to ours, we can say, well, in your test environment, how does that compare to your production environment? So that would give us a bit of a scale factor. We may also want to write some spiked kind of tests that we can run on our test hardware and on our production hardware if we can get a hold of borrow it for a little while. To say, well, how much faster do database calls go on this machine versus that one? And we don't want to get too fooled about the kind of precision we're getting, but we can get some kind of order of magnitude number, like it's twice as fast, or it's about the same, or it's 10 times faster. And we can feel much more comfortable when we say, well, performance seems to be acceptable in test, so therefore we think it's going to be acceptable in production. One of the things we can take advantage of when setting up this type of production-like environment is what I call the performance step graph. Quite often, if you graph performance, let's say elapsed time this way and kind of amount of work you're doing this way, you will often, rather than it being like a straight curve, quite often what you'll see is like a staircase. Let's take a database system, for example. If we're running in a database system with 5 or 10 rows in it, we'll get really good response. And as we continue to add rows to that database, we'll continue to get really good response, basically because everything is staying in memory. We're not having to do disk I/O. The database server can hold 1,000 rows, 10,000 rows in memory. And so even if we go from 1 row to 10,000 rows, we'll probably see barely perceptible degradation of performance. Somewhere out around, well, it depends, of course, on lots of things, your hardware and memory and so on, but say 100,000 or 1 million rows will suddenly start having more data than it can hold in memory. It will be starting to write things out to disk and fetch things from disk. And we'll see a dramatic drop in performance. But once we've taken that hit, we'll see it stay, again, relatively flat for a long time. Because now we're going to disk, and the disk has a certain speed, a certain access time, and it doesn't matter if there's 1 million rows out there or 100 million rows out there. We'll see a relatively flat curve, or a flat graph. So if we can find out where that first step happens, say at 1 million rows, then we can set up a test database with 1 million rows in it. And even if in production we expect 100 million rows, we know we don't have to populate this with 100 million rows to get good feedback, as long as we know we're up that first step. So that's what I mean by step up the performance graph. There may be some things that we can't reasonably duplicate on a regular basis in a test environment. Say we're expecting 10,000 simultaneous users to access the system. We can't, on a regular basis, round up 10,000 people to sit down and test it. So we may need to do specific times when we do load tests, when we simulate the load of lots of people on the system. And we need to cooperate and collaborate with the customers and the testers who are testing the system to arrange those types of things. It's, of course, not a case that we're just throwing it over the wall to them and saying, okay, we're finished with development, you test it and tell us if there's any performance problems. We want to make sure that they're having a chance to give us the kind of information that's useful back, that we're getting the kind of feedback that we need. Okay, so it's slow, now what? How many people here like to do Sudoku problems? Okay, I want you guys to be doing performance tuning for me. Performance tuning is problem solving. Perhaps, in my biased opinion, the purest form of performance solving, the most fun, I think, in software development, because it's evidence-based. We're collecting information, we're analyzing that information, we're developing a hypothesis, we're testing that hypothesis, we're getting this feedback. It's the scientific process. So in order to carry out this empirical process, we need data. So we need to be able to measure more than just a customer saying, oh, it's too slow. We need to be able to measure and say, well, specifically, how slow is it and where is it slow? Because until we know where it's slow, we can't improve performance. Now, my experience, well, although there's many specialized performance testing tools out there, I've had the best success with simple wall clock tests. By wall clock, I mean, usually it's not the wall actually, but wristwatch tests. So you run a particular test that you know is doing certain things, and you watch and see how long it takes to run. As I say, there are specialized tools. I'll tell you one little story about perhaps my first major encounter with specialized tools. We were working on a Java system and it was running too slow. So we got this Java performance profiler tool. We installed it and figured out how to run it and collect information from it. And so it gathers this vast volume of information. We figure out how to analyze this. And after several days, it comes back and says, your system is spending 95% of its time in some JDBC, blah, 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 something or other class. In other words, waiting for the database to do something. So I spent several days finding out that the problem wasn't even where I was looking at it, that the tool I'm using is absolutely useless in helping me find it. So now I need to go over to the database guys and say, oh, can you set up all your database performance monitoring tools and blah, blah, blah. We'll reproduce the whole process again and you'll produce all this information and come back and say, well, you're doing too many joins on this particular query, blah, 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 blah. But that hasn't really helped me either, because now I need to know, well, where in my code, why is it doing this? And why is my object relation mapping software generating that SQL? So anyway, to cut a long story short, I could have found out that same information, I think, in half a day by doing specific targeted tests and just measuring. Let me run this thing with the database locked out. Whoa, that's really fast. So I guess that part of it wasn't the problem. Well, let me run a little driver that just runs those databases. The portion of the system that does those databases goes, whoa, that's really slow. Okay, let me do this, start subdividing and working my way down through, and I can gather the information I need a lot quicker. If you run up against a wall where that simple technique isn't working, then start looking for the specialized tools. One caveat when measuring performance is what I call the first time penalty and the second time dividend. Much of modern software architectures and tools and hardware and blah, blah, blah tends to be slow the first time you do something. So a just-in-time compiler that happens when you first load some .NET or some Java code, that's a cost that isn't incurred the second time you use it. The first time you go after some specific information from a database, it pulls it from disk, but then it holds it in buffers and cache and memory, so the second time you go, that'll be much faster. So how do you compensate for this? Pretty simply, just run your tests 10 times and average them, or something like that. Or run it once, and then run it again, and don't be surprised if you see this slow and then fast. So, my mantra for performance tuning, analogous to red-green refactor, is measure, think, measure. You can measure what's happening with the system. I talked a little bit about how to measure previously and how not to get too involved in tools. So one of the first things we can do when we're trying to figure out where our performance problem is just basic exploratory testing on the system. The customer says, the customer inquiry is too slow. Okay, is that on all customers? Is it perhaps on large customers with lots of orders? Is it on inactive customers? Even before we start digging into the code, we can gather a lot of information. We can get our test people, I mean, they're expert at doing this, to help us drill down and narrow down the focus of where we start looking. Once we get into the code, again, as I said before, we start exercising smaller and smaller portions of the code until we find where the bottleneck is. Mock out this part, mock out that part. Run the first half of this process, run the second half of this process. Which one is fast, which one is slow? Once we've identified an area that's slow, we need to fix it. So this is the think part. We need to think about it. Why is this slow? What are some alternate things we can do? But then we need to measure again. So we don't just say, oh, I bet this is the fix. Tack it in there. Okay, now we're done. We need to prototype and measure an alternate strategy, and if that solves the problem, great. If it doesn't, then we've got to think some more. So in this continuous process, getting information, developing hypotheses, proving or disproving those hypotheses. These are a few anti-patterns that I've observed. Google paste and pray. I'm not a big fan of it, but there are some situations where it works. This, of course, is you're looking for a problem, so you Google until you find some sample code. You cut and paste that code into your program, and then you pray that that's fixed your problem. This is never going to work when you're performance tuning. This may help when you're trying to figure out how to use a particular API or how to get some functionality working in your program. But your performance problem is never going to be the same as someone else's performance. I was looking actually on Google, one of the mailing lists that I frequent. Someone was complaining. They posted a question saying, my ASP.NET page's loading is too slow. And people started coming back with all kinds of useful information about how the page flow and data pipeline of ASP.NET works, and it could be in your page init and your page load and blah, blah, blah. And I thought, well, yeah, it could be in any of those, but maybe it's because you're reading a million rows from the database before you load the page. So, Google is not really going to help you a lot. Another anti-pattern is performance folklore. Stored procedures. How many people believe the statement that stored procedures are the only way to get good performance out of database access? Not quite so current anymore as it used to be. But there are still shops, I know, maybe if anyone here is in one of them, you feel like you don't want to admit it, that have standards that say, all database access must be done in stored procedures. Why? Oh, because of performance. Performance folklore. In certain specific situations it may be true. In most situations it isn't. And at one point in time it may have been true, but now maybe it isn't. That kind of brings me to the third anti-pattern, which is short shelf life. Performance of hardware and software infrastructure, its characteristics are changing all the time. And always beware of trying to do the same thing that you used to solve a problem last year, trying to apply the same solution to this year, because it may work, but there's no particular reason to believe it will. So, once we've figured out where the bottleneck is, we want to make changes, we still want to keep it clean. It's not an excuse to make a mess. As one famous alpha ape said, if it was hard to write, it should be hard to read. It's not the attitude we need for code in any case, and specifically, especially not when we're making performance modifications. We have the techniques to encapsulate complexity. Oh, you know that guy. We have techniques for producing clean code that we use to encapsulate complexity and things like that. We use those same techniques to encapsulate performance-sensitive kinds of stuff that you've done. Use the same techniques you use to make your code understandable. If you have to write a particularly obscure function to do something, then name that function to say, this is calculating the blah, blah, blah to improve performance, or even put a comment in so people know what you're doing. Clean code is tunable code. I was going to do my Uncle Bob impression, but I don't think I can match what Fowler did at this point. And once we've got it fast, we want to keep it fast. So in the same way that we use unit tests and acceptance tests to give us a regression test suite for our functional characteristics of our system, we can do the same thing with performance characteristics. Tools like an XUnit or FIT or whatever you use, in my experience, work just fine for this as well. You're doing the same kind of thing, that exercise some code given some inputs, only instead of asserting that some output is functionally correct, you're just asserting that the elapsed time it took is under a certain number, for example. It's a bit of an issue because performance is not really a red-green thing. In some cases it is. If you have absolute hard, like on our train control system, it has to be under 1 second or we can't deploy. Often there's a little more wiggle room in here, and these testing tools don't really have a nice way to say red, green, or yellow sort of thing to say, well, this has fallen into the warning area, so you may have to hack a little bit. First of all, you may not care. You can say, well, as long as it's under a certain thing, we'll consider it green and we won't worry about it unless it goes red. Or you can have a couple of test suites, one of which is your critical measures, and if that goes red, you've got a problem. You can have another test suite, which is kind of like your warning level. So if failures in there aren't enough to cause you to not deploy, but just kind of a heads up that something's starting to go a little slow in this area, we may want to look at it. So there's a couple of things you can do there. I wouldn't run this as part of continuous integration for a couple of reasons. First of all, it's likely not to be a fast suite because you're doing all those things that they say don't do in your unit test, like accessing the database and whatever. So we're not trying to make this be a fast suite because it's trying to do a lot of work and see how long it takes. And we're probably, again, we may have this test database we have set up, configured a certain way with our million rows in it and stuff like that we don't want to be using for continuous integration. But we do want to run it regularly to make sure things are okay.
Like what's regularly in your best practice?
Once at like kind of the end of an iteration, as you're coming to the end of an iteration. When some new functionality has been mostly built. So, I've been talking in kind of generalities so far. So, for the people who want a little raw meat, I'm going to talk about a few specific patterns for performance tuning. But with a couple of caveats. Remember what I said about short shelf life. It's really hard to say. Fast, short shelf life. So these things over time tend to become less true or tend to change. And like any type of pattern, like design patterns, these are more to generate ideas and generate a thought process than they are to be applied religiously. So use them that way as a springboard for ideas. First one is what's been called the performance hierarchy. So this says that going from fastest to slowest, to access code or data in the same process memory that I'm currently in is the fastest we can do. If we have to go over to another process's memory space, but on the same machine, that's a little slower, but it's still pretty good. If we have to go to another process's memory on another machine across the network, then that's slower. If the information we need or the code we need is not in memory anywhere but on disk, then that's worst of all. So obviously, if we have a performance bottleneck, we want to say, well, is that because we're too far down on this hierarchy? Is there some way we can move ourselves up the hierarchy? This is tending to be less clear-cut nowadays than it used to be. With the prevalence of machines with multiple CPUs, the overhead to get to another process is often not as much as it used to be. When we had a single CPU, the operating system basically had to suspend the operation of the current process and move all the registers and stuff and save them somewhere, and then bring in the context of this other process and let it start executing in order for it to process this request we sent it, and then suspend its operation and save all its current state and bring our current state back in so we can receive this reply from it. If we have enough CPUs that the processes are each on their own CPU, we don't incur so much of that context switching overhead. We still have some overhead to transfer the data. So the gap between those two is, in some cases, less clear-cut than it used to be. And of course, if we're on another machine, it makes a big difference whether we're on some gigabit network in the server room like 2 feet away, connected by fiber optics, or whether the machine is out on the internet somewhere where who knows what the response time will be. And even with this, with solid-state disks now becoming inexpensive enough for lots of applications, that there's no longer such a difference between being on disk and being in memory. So again, all these things you need to measure, of course, to figure out what your specific situation is. But what we tend to do is try to avoid going further down that hierarchy. And the other thing is, if we have to go down the hierarchy a ways, if we have to go over to another machine over the network, let's try and do as much stuff as we can on that trip. While it may be slow to go to another machine once, it's even worse if we're going to go to that machine 10 times. It's better to pass back a bunch of data, even more data than we need, if we can do it in one round trip than in 10 small trips. It's often, if we actually have to go to disk and read a bunch of data in, it's not that much more to read. Once we've got the disk head over there in position and it's starting to read the data, it doesn't cost us that much more to read more data. So grab everything we can while we're over there. Okay. Here's another classic. Loop invariant. So this classically this is the idea that an inexpensive operation being performed inside a loop where nothing that's happening inside the loop is changing the inputs to that operation. It means we can move the operation outside the loop and only do it once. In the very simple case of like inside a loop, you're adding 2 numbers together and the 2 numbers are actually from outside the loop. Well, yes, you could put them in a temporary variable and then just save doing that addition each time. But modern compilers will optimize those, in most cases, optimize those simple cases away. So you need to look for perhaps more non-obvious cases. You're going through processing, in a loop, processing a customer's invoices, and you're reading the customer address every time through this loop, even though the customer address doesn't change. The compiler obviously can't know that because you're going after the database. But you can look for cases like that, and it's surprising what you'll find sometimes. Lazy load. So again, trying to avoid doing an expensive operation. This is the case where an expensive operation is performed at the start of something, the loading of a class or the starting up of a program. But that the results of that operation may not be needed until later, in fact, may not be needed at all. And so, if we can avoid doing this expensive operation until we need it, quite often we can save. And once we do it, we save the results of it, so next time we don't have to do it again. So this leads us to an extension of that kind of idea, that if we've done an expensive operation, well, let's try and keep it around and try not to have to do it again. So we have the concept of caching. So we save the results of whatever this expensive operation is. When I say expensive operation, could be CPU intensive calculation, could be going to the database, anything on that performance hierarchy as well, going across the network to get some information on the machine, going to disk to get something. As we have more and more memory available to us, we can start thinking of the concept of what I call a very large cache, which is we save everything that we do. Typically a cache has a certain size, and when the cache is full and you do another operation, you need some kind of algorithm to decide, okay, who am I going to throw away to make room for this new guy? And often it's on a most recently used basis, so the oldest one gets thrown out. The idea of a very large cache is you never throw anything away, you just keep it. You always keep it. The big issue with caches is, of course, how do you detect when that result is still valid? This operation has taken in certain inputs. What if those, you have to have some way of knowing when those inputs have changed so you can invalidate an entry in a cache and throw it away so it'll be recalculated. So while it seems like a great idea, it can start to get more complicated. Another pattern is asynchronous processing. So the idea here is similar to our rail traffic control system. Do just the minimum we need to sort of persist the results of something into a queue and push it off to be done later. So the customer can go on to something else and we'll get to this as soon as we can. Often, if we can identify operations like that can be pushed off into this queue, it can give us, there's all kinds of nice things we can do with queues. We're able to parallelize the processing of results out of that queue. So we can get good throughput and stuff like that. The trade-off here is that often we need some way, in some cases we don't, but often we need to be able to notify the customer or deliver the results to them later in some kind of form, because we weren't able to do that immediately. And this brings me to perhaps one of the most powerful performance tuning techniques, which actually often doesn't involve necessarily making anything run faster, which is the whole design of the user experience or user interface. Can often go a long way to improving system performance. If we have a screen that's crammed full of all kinds of data, so that whatever the user wants, they have this general dashboard type screen, they can look, oh, that's here, that's here, that's here, but most of the time they only want one particular piece of information on there. We might want to think about whether that's actually the best way to approach that. Maybe we want some disclosure where the drill down, where they focus on, they kind of indicate what information they're interested in, and we give them some kind of short form or summary of it, and then if they're interested, they can drill down, we can give them more detail. So we're doing kind of like a lazy load. We're putting off the expensive operations until the user tells us they really need it. The other thing in user experience design is the idea of establishing a workflow rhythm. When people use a computer system, it's quite often they have a type of work where they're heads down, do this, do this, do this, do this. And then they've reached a point where they've completed a chunk of work. They feel they've earned themselves a little break, and then they're quite happy at that point to say, okay, submit, send, whatever, sit back, reach for the coffee, and let the system tick away for a little while. So we might have a situation where they go through 5 screens to do this, and say our performance is 3 seconds on each one. So total elapsed time, 15 seconds it takes them to work through this process. If the operation they're doing is in that kind of a rhythm, they're going to feel, oh, it's so slow, there's 3 seconds I have to wait, I want to get to the next one. 3 seconds I have to wait again. And then at the end, that last 3 seconds, they don't care that it's 3 seconds. It would be much better for perceived performance if it was 1 second, 1 second, 1 second, then when we're left with 11 seconds on the last one. They'd be happy with that. Say, great responsive system. I go bang, 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 and rest. I mean, the best example I could come up with off the top of my head was I'm on Amazon and I'm looking for a book. So I'm going to search. I want that quick response. I don't want to be sitting there. Oh my God, how long is it going to take to bring this book up? I just want to pick it. And then I go in and enter my credit card information or do the one button, whatever, blah, blah, blah. Once I've picked my books and filled up my checkout cart, then I'm done. I'm quite happy to sit back while it processes my credit card and ticks away there. I don't mind that part of the system is slow because I've completed my task and I want a little rest before I move on to my next one. So as I say, this can be a very powerful technique for performance tuning. But I would offer the big caveat that don't go to this until you have done the measure and think part first, until you've identified the bottleneck. You don't want to always be going to your users, your customers, as soon as they say, oh, there's a performance problem here, and you tell them, well, you just need to have less information on that screen, or you need to, or whatever. You don't want to immediately go right away to say, oh, well, that's because we need to change your user interface, because maybe it's something stupid that you've done. Once you've eliminated that, and you're faced with perhaps some difficult decisions about how could I give them this kind of performance? I'm going to have to do all kinds of complicated stuff. It's worth asking, do you really need this? Because quite often the answer is, well, no, I can wait for that. Okay, this is my last one, I think. Library framework overhead. By library, I mean library, something that my software calls and does something for me. Framework, something that kind of exists, I exist within it, and it kind of calls me to do some kind of stuff. But a similar concept. Using the wrong tool can often be a big issue. I've seen systems, this again is less prevalent than it used to be. When XML first came out, people wanted to use XML everywhere. What a great idea. You'd see a method signature like returns XML, takes in a single parameter full of XML. This great general purpose method. I can change the parameters like on the fly at any point in time. The results can morph into anything. But I mean, never mind the system design implications of that, but just the overhead of parsing this XML document every time in order to pick out a couple of parameters, assembling your result back into another XML document to return it. Just have the caller have to parse apart that XML document to pick out things. It's using the wrong tool in the wrong place. Frameworks, again, we use them because of the productivity that they give us. We have to do less work because this flexible framework does all this stuff for us, and we just have to stick in our particular screen layout or something like that. Most of the time, frameworks are more flexible than we need. They're doing more stuff than we need because they need to appeal to a wide base of people doing all kinds of things. And our particular niche fits in there, but the framework's often doing a lot of extra work that we don't need. And quite often that doesn't matter because our performance is still acceptable. What you want to look for in frameworks is what I call user exit points, not being an end user, but you, the programmer, is the user of the framework. Do they have some way where, if necessary, you can bypass their processing or stick your own code in to do something? One example I can give of that is, this is Windows.NET specific, but the WinForms, which is the framework that we use to develop GUI screens within .NET, handles all the actual I/O to the screen for you. It takes that away from you because for good reason, so you don't have to worry about it. But you can always get a hold of the actual low-level Windows handle if you need it. And you can do any kind of low-level stuff you need to the screen if you really need to. So that's a framework that takes all the extra work away from you when you don't want to do it, but gives you this user exit, I call it, this way to reach down through the framework or up through the framework or whatever direction it is to get your work done if you need to. Okay. So the performance engineer, much as he loved to do all that math, the performance superhero have retired. We can use the same principles that we use as Agile developers to approach the problem of performance tuning. And instead of being afraid of performance, we can turn it into a competitive advantage. It means we can deliver, if we're pressing right up against the limits of hardware, we can deliver sooner if we can optimize the use of that hardware better than our competitors are and get something out before, well, they have to wait for hardware. Or we can do it, if we're not at that edge, we can do it cheaper perhaps, using smaller servers, smaller desktops, that sort of thing. We have 5 minutes. Any questions, any comments? Yes.
Is there any best practice that you are following? Let's say that we have a situation that it is not obvious what the problem, like it's not database call, it's not network call. I mean, it's not obvious disk calls or anything. So what are you looking in the code as best practice? I mean, are you looking at the data structures or the logic that is the algorithm is doing?
What I do, the question was,
From your experience.
yeah, if you don't know where the problem is in the code, where you start to look. What I do, if I don't know where the problem is in the code, means I need to do more measurement. So I do this drill down through the code, this divide and conquer of the code. So I run a test that executes a chunk of code, maybe like the whole customer query all the way through down to the database, whatever, and it comes back. And it's too slow, it takes 10 seconds. So I chop out part, I chop out the database, I mock it out, execute it again. So now I'm just executing like, the top part of the code, not the database part. How long does that take? 0.3 seconds. Whoa, it's a database problem. Or I execute that top part of code and it's 9.7 seconds. Okay, database is fine, but it's somewhere in here. Okay, break off this chunk and execute it. 0.2 seconds. Okay, it's not there. And just keep searching your way through the exploratory testing your way through the code until you can get it down to something small enough. And by that time, it's usually obvious. Once you get it down to a small enough piece, you see, oh, I see. It's doing this database call that's really slow, or it's going across the network 100 times and I want it to do it once. Or it goes into this loop that processes something 1,000,000 times.
I want to add one more thing that sometimes it's still not obvious. Like you are doing these chunks of code, you are creating tests for each this part, but sometimes the problem occurs within, let's say, 10,000 concurrent users. If there is such a case, then the problem occurs. So all these tests are like multi-threaded tests, or how are you doing this thing? Or you are just using like big sealing tools and just chunks, and because like from my experience, like we are trying to do these things and most of the time like there's no performance problem in the code. But actually after a while we investigate the thing and we do these multi-threaded things and we are doing load testing and stuff, and we find out that there is this data structure which was wrong. They were using, let's say, I don't know, hash table instead of a hash map, for instance, which the algorithm totally changed. And so there are things like that. So are you using anything like this, or I don't know, like
in that type of situation, I think I would try, again, if it only occurs under multi-threaded situation, I would try to write tests to do that, to like spawn off 1,000 threads or something of the execution of it. And if I could only replicate it in that situation, I might add logging information to like put little measurement things in a chunk of my code. So elapsed time. What's the elapsed time in this piece of code here? But I'm collecting. So I got 1,000 threads going. I'm collecting thousands and thousands of these for all of just some kind of log file, and then it's laborious sometimes. You start pouring through that log file and trying to say, what does this mean? How come it's slow here between these points only under this load, that sort of thing.
So you try to get as much as information.
Yeah. If the simple clock time doesn't tell you, then start logging
Okay.
much more incremental times inside.
So from your experience, how do you prioritize, like usually what you're testing? Are you going for database first and then network after? Like usually where the big bottlenecks are? Do you have an order or recipe set where you decide you always go for database check, making sure that
I try not to do that because the question is, what is my priority order when I go through what areas do I look at first? I try not to always look for database first and whatever. I mean, I'm starting from some perception either through end user or through some specific performance test we did that. This end-to-end chunk is too slow. So, as I said before, I try to drill down, narrow down, focus in on one areas and not jump to any specific area first. I mean, an obvious area to chop off is to mock out database or network access first. But I don't jump to a quick conclusion. I've done that before. I was working on one problem where database, I saw that the database, the problem was in the area of the code that was accessing the database. So I said, oh, something's wrong with my query. So I started running query plans and using database tools to tell me what the database was doing with this. And it looked fine. What's wrong? I finally discovered that I had screwed something up with connection pooling. So connection pooling is where rather than having to connect to the database every time you make a single call, it's like a cache. You connect once, and it does all your database calls and uses the connection out of the pool. I had screwed this up, so I was having to connect to the database every time. But I immediately jumped to the conclusion that something was wrong with my SQL. I was starting to analyze and spend a half a day actually trying to figure out what's wrong with my SQL before I did some more fine-grained logging and testing to narrow down, oh, it's the connect statement. So why should that be so? So, short answer is I try to avoid any kind of preconceived idea about where the problem might be.
you don't follow intuition, you really try a more rigorous method?
Yes.
Okay. Answer.
Yes.
I just have a question about stored procedures and the performance thing, and I agree they're not necessarily always faster. So my comment is that, I'm one of the database people, so when there's a performance issue, it always comes to me. And if I see the queries running slowly, quite often I go, oh, thank God it's in a stored procedure, because if it's a customer critical issue, and I found it easier and less risky to tune and deliver them just a new stored procedure than if the business layer, the DLL, is building the SQL dynamically, and now we have to build them a new DLL and that sort of thing. So I'm just wondering if you could comment on that. If stored.
Yes, a couple of things about stored procedures. I didn't say that stored procedures weren't faster than dynamic SQL. What I said was nowadays they are rarely the cause of a performance problem. Stored procedures are almost always faster, but not measurably, not enough faster that it's usually a problem. And there's a couple of problems with using stored procedures. One is they often don't play well with a lot of the productivity tools, the object relational mappers and so on. And the other thing is that people often end up, because they have the capabilities to do more than just execute SQL, and people start pushing business logic down into them, and we end up with poorly structured systems. So, but that's not really a reason. I mean, if you could enforce the discipline not to do that, it's not a reason not to use stored procedures. Yeah, I worked at a shop where actually I was pushing against the project manager because they had always written all this stuff, not just their database access, but all this business logic inside stored procedures. And the project manager said, oh yeah, we like to do that because it's so much easier to deploy it to production. Because the DB, it does build a stored procedure or whatever you do, compile it or something, and the DBA just moves it over to the production database. Whereas if we actually have to change our code, we have to go through all these approvals and deployment, and the server people all have to be involved. Well, the problem there is not with the fact that C# code or Java code isn't necessarily any harder to deploy. It's because you have a broken build process, that it just happens to be an artifact of a broken organization that stored procedures, we can push them right in. Why should they have any less rigorous a procedure than pushing DLLs out, right? So, I can't remember what your original question was.
Well, I was just commenting about, because, you know, in our organization, it is perceived, I mean, we still test the stored procedure, go through all the testing, but, you know, it's just perceived as a little less risky to stored procedure.
Yeah, so I think,
And maybe that's
I think
false
you need, your
perception.
organization needs to work on making it less risky to deploy other code. Yeah. And streamlining that process so that the decision that's made isn't based on what's easier to deploy. The decision's made on more sound software principles about where does this functionality belong.
So, comment on the question. I really like your point about dividing up the problem dividing up the problem and the importance of having data. I build systems that have to handle hundreds of thousands of transactions a second. And so when we do something like that, we need to have information. We need to have information available to you all the time. So we can be very careful, instrument code, but in a non-intrusive way, right? Because if what you don't want to have is the logging creating the problem, finding out that there's logging is the problem, right? But it's interesting when you see someone who's confronting a performance problem for the first time, because they literally don't know where to start. And as you point out, it's a path right from here to here. So divide it. Okay, was it between here and here? No. Is it between here and here? Okay, divide it. Find logical places along that path and have some information that you can use to attack it. I think that's a good point. And I see too many systems that are deployed, enterprise systems that are deployed without some kind of instrumentation. So you have to start from scratch with all that instrumentation.
Okay, we're past time, so thank you very much.